There is a moment in science that happens occasionally, not often, but often enough that historians have given it a name. It's the moment when an instrument designed to confirm what we already believe instead returns data that makes the people reading it go quiet. Not the quiet of confusion. The quiet of people who have just realised that something they assumed was settled is not settled at all. James Webb was supposed to confirm the standard model of cosmology. That was, in a meaningful sense, part of its mission. We had built a picture of how the early universe looked, how the first stars ignited, how the first galaxies assembled, and Webb was going to let us see it directly for the first time, filling in the details of a story we thought we already knew. Instead, in observation after observation, Webb has been returning data that doesn't fit the story. Not in small ways. Not the kind of minor discrepancies corrected with a tweak to the parameters. In ways that have cosmologists revisiting assumptions they've held for decades. In ways that have produced a phrase you almost never hear from careful scientists working in a field built on precision. We didn't expect this. Let me walk you through what Webb's been finding, the specific observations, what they mean, and why the collective weight of them is beginning to feel less like a collection of anomalies and more like a message the universe is trying to send us. Let's start with the galaxies. This is where the surprise began, and it still generates the most debate. In the standard model, the universe begins with the Big Bang and expands and cools over time. In the first few 100,000 years, it's a hot plasma, opaque to light. Then it cools enough for atoms to form, light is released, and the universe enters the Dark Ages, a period before any stars exist, when the cosmos is filled only with hydrogen gas slowly clumping under gravity. The first stars, population 3, are thought to have ignited around 100 to 200 million years after the Big Bang. Massive, hot, short-lived. The first galaxies began assembling shortly after, growing gradually through mergers and accretion over hundreds of millions of years. This process, gradual, building up from smaller pieces over long timescales, is called hierarchical structure formation. It's a key prediction of the standard model, and it predicts what galaxies at high redshift should look like: small, irregular, still assembling, still accumulating their stars. What Webb found was something different. In its first deep field images, released in summer 2022, Webb detected galaxies from the first 500 to 700 million years of the universe. Galaxies that should have been small, irregular, still forming. Instead, some were massive, structurally mature, containing hundreds of billions of stars, with organised forms, spirals, ellipticals, clear bulge disk structures that in our local universe take billions of years to develop. One astronomer involved in the initial analysis put it plainly: we found galaxies that simply should not exist at this epoch in the universe. The timescale doesn't work. That's the core of the problem. Building a massive, mature galaxy takes time. You need stars to form, live and die. You need successive generations enriching the interstellar medium. You need mergers and gravitational settling to organise the structure. The standard model gives you a budget of time for each process, and the galaxies Webb is finding appear to have done in 500 million years what the model says should take several billion. The initial reaction was cautious. Redshift measurements can be uncertain at very high redshifts. Maybe some objects weren't as distant as the estimates suggested. Maybe the mass estimates were off. Maybe observational biases made young galaxies look more structured than they were. So the follow-up work began. More precise spectroscopic measurements confirmed the redshifts. Mass estimates were refined with multiple independent techniques. Other groups analysed the same data. The galaxies held up. The redshifts were confirmed. The masses were real. The structures were genuine. And as more Webb data came in, more of them showed up. By 2024, there were dozens of confirmed massive early galaxies. By 2025, with Cosmos Webb, the largest systematic Webb survey ever conducted, mapping hundreds of thousands of galaxies, the tension had sharpened into something harder to dismiss. The universe, at a time when it should have been in the early stages of galaxy assembly, was already full of galaxies that looked like they'd been assembling for much longer than the timeline allows. Now here's where it gets more interesting. The existence of massive early galaxies is surprising, but not necessarily fatal to the standard model by itself. There are mechanisms that could, in principle, produce faster forming galaxies. Unusually dense regions could have collapsed more efficiently. Feedback from early stars might have behaved differently. Dark matter halos might have scaffolded unusually rapid assembly in certain regions. These are genuine possibilities, and some of the tension may well be resolved within the existing framework. But here is what's harder to explain away. It's not just the existence of these galaxies. It's their chemistry. The first stars were made almost entirely of hydrogen and helium, the only elements that existed in quantity after the Big Bang. As they died, they seeded the universe with heavier elements through supernovae. Each subsequent generation was born from enriched gas producing stars with progressively higher metallicity, the abundance of elements heavier than helium. This enrichment takes time. Multiple generations of stellar birth and death. The standard model predicts early galaxies should be metal poor. Webb has found early galaxies with metallicities comparable to galaxies in the local universe, galaxies that have had 13 billion years of stellar generations to enrich themselves. Galaxies in the first billion years with the chemical complexity of galaxies orders of magnitude older. This is the piece that doesn't bend. You can adjust your models to make galaxies form faster. You cannot easily make the universe generate multiple generations of stellar evolution in the time available. The chemistry is a timestamp, and the timestamps don't match. There's a third observation I want to discuss, one that gets less attention than the galaxy-sized problem, but which, to some cosmologists, is even more troubling. The cosmic dawn. In the standard model, the dark ages end when the first stars and galaxies ionize the surrounding neutral hydrogen, a process called reionization, over a period stretching roughly from 150 million to 1 billion years after the Big Bang. This is one of the most precisely modelled epochs in cosmological history. Webb is finding that the sources responsible for reionization are more numerous and more luminous at very high redshifts than the models predict. There are more of them, they're brighter, and they appear earlier than the timeline suggests they should. This connects directly to the massive galaxy problem. If early galaxies formed faster and reached higher luminosities sooner, they would ionize the surrounding gas faster than the models suggest. The epoch of cosmic dawn might have been brighter, earlier, and more complex than we thought. So the surprises aren't isolated. They're connected. The same underlying mechanism, whatever is causing galaxies to form and evolve faster than predicted, is showing up across multiple independent observational lines. Massive early galaxies, unexpected metallicities, earlier, brighter reionization. The observations all point in the same direction. So what is that mechanism? What could explain a universe that builds structure and chemistry faster than our best models predict? There are several serious proposals being investigated. The first involves the efficiency of star formation. Our models are calibrated against the local universe, where conditions are very different from the early cosmos. Gas density, radiation strength, turbulence all affect how efficiently gas collapses into stars. In the extreme conditions of the early universe, star formation may have proceeded far more efficiently, letting galaxies assemble in a fraction of the predicted time. The second involves dark matter. The standard model uses cold dark matter with specific clustering properties. Alternative models, warm dark matter, certain self-interacting variants, predict different small-scale behavior that could accelerate the formation of the most massive early structures. The galaxy-sized problem might be telling us about the nature of dark matter itself. The third is the most radical, and a small but growing number of cosmologists are taking it seriously. The expansion history of the early universe might differ from what the standard model assumes. There's already a documented Hubble tension, a disagreement between measurements of the universe's expansion rate. If the universe expanded differently in its first few 100 million years than lambda CDM predicts, the available time for structure formation changes, and these galaxies might not be as anomalously old as they appear. None of these is established. All require modifications or extensions to the standard model, but all are grounded in legitimate theory, and all are being tested against Webb's ongoing observations. I want to be careful about what we're saying and not saying. The standard model, lambda CDM, is not broken. It is not about to be thrown out. It's one of the most successful scientific theories ever constructed, with decades of predictive success across an enormous range of observations. The cosmic microwave background, Big Bang nucleosynthesis, the large-scale distribution of galaxies, the accelerating expansion. On all these fronts, it works extraordinarily well. What Webb is revealing is not that the model is wrong. It's that the model is incomplete. That the story of Cosmic Dawn, the first chapter of the universe's history, is more complex, more eventful, and more surprising than we anticipated. This isn't a failure of cosmology. It's cosmology working exactly as it should, building a theory, testing it against the best observations, and following the data wherever it leads. And right now, the data is leading somewhere new. There's something genuinely moving about where we are. For the first time in human history, we are actually seeing the early universe. Not inferring it. Not simulating it. Seeing it, the actual light from the actual first galaxies captured by a telescope that took decades to build and now sits over 1 million kilometers from Earth, operating near absolute zero, sensitive to wavelengths invisible to human eyes. And what we're seeing is not quite what we expected. The early universe was stranger than we thought. More active. More structured. More chemically complex. It assembled itself faster than our models predicted, built galaxies our timeline says shouldn't exist, and illuminated itself sooner and more brightly than we anticipated. These surprises are not problems to be embarrassed about. They are gifts. They are the universe telling us our picture is incomplete, that there is more to understand, more to discover, more to revise. Every time Webb returns data that makes cosmologists stop and think, it is doing exactly what the greatest scientific instruments always do. It is not confirming the expected. It is expanding the possible. Let me leave you with one image that captures where we are better than any statistic. When Webb returned its first deep field, that patch of sky no bigger than a grain of sand held at arm's length, filled with thousands of galaxies, one scientist on the team described what it felt like to look at it. She said it felt like opening a window into a room she'd been hearing sounds from for years, the muffled, indirect evidence of the microwave background, of quasar spectra, of gravitational lensing, and finally being able to see inside. And what she saw was not the simple, orderly room the models had led her to expect. It was something far more complex, far more active, far more alive. That image contains galaxies from every epoch, a cross-section of 13 billion years captured in a single exposure. And scattered at the greatest distances are those early galaxies that shouldn't be as massive, as structured, as chemically complex as they are. They are there, in the data, real, confirmed, waiting to be explained. And the explanation, when it comes, will tell us something fundamental we do not yet know. Something about how matter assembles under gravity. Something about dark matter and dark energy. Something possibly about the expansion history of the cosmos in its earliest moments. We are not refining a complete picture. We are discovering that the picture was always a sketch, a first approximation of something far richer, far stranger, and far more interesting than we had allowed ourselves to imagine. James Webb didn't just give us better images of the early universe. It gave us better questions. And in science, a better question is always the beginning of something new. The early universe is not what we thought it was. What it actually is, we are still finding out. It was stranger. It was richer. It was more alive. And we are only just beginning to understand what it means.